power supplies, which are devices which maintain a constant potential difference. Here we have such a power supply, potential difference V, this be the plus side, and this be the minus side. I'm going to connect this. I have a resistor here, R, and as a result of this, a current will start to flow in this direction, this direction, this direction. So in the power supply, the current flows in this direction. Through the resistance, the current flows in this direction. In what direction is the electric field? The electric field always runs from plus to minus potential. So right here in this resistor, the electric field is in this direction, from plus to minus. But inside the supply, it must also go from plus to minus. And so inside the supply, the electric field is in the direction that opposes the current. So some kind of a pump mechanism must force the current to go inside the supply against the electric field. A boulder does not all by itself move up a hill. And so something is needed to push it. You remember with the Van de Graaff, we were spraying charge onto a belt. And then we rotated the belt. And the belt forces the charge into the dome. It had to overcome the repelling force of the dome. So work had to be done. So the energy must come from somewhere. And in the case of the Van de Graaff, it was clearly the motor that kept the belt running. In the case of the Wimhurst, it was I who turned the crank. So I did work. In the case of common batteries, the ones that you buy in the store, it is chemical energy that provides the energy. And I will discuss now with you and demonstrate a particular kind of chemical energy, which is one whereby we have a zinc and a copper plate in a solution. So we have here H2SO4, and we have here a zinc plate, and we have here a copper plate. This side will become positive, and this side will become negative. You will get a potential difference between these two plates. To understand that really takes quantum mechanics. This goes beyond this course. But the potential difference that you get is normally something around 1 volt. The secret really is not necessarily in the solution, because if you take two different conductors, and you touch them metal on metal, there will also be a potential difference. So let's look at this now in some more detail. We have here a porous barrier that the ions can flow freely from one side to the other. And we connect them here with a resistor. And so a current is now flowing. A current is flowing in this direction through the resistor, from the plus side of the battery to the minus side. That means inside the battery the current is flowing like this. And the electric field here is in this direction, from plus to minus, but also inside the battery the electric field must be from plus to minus. So you see again, as we saw here, that the electric field is in the opposite direction of the current. You will have here SO4 minus ions, and you have copper plus ions in this solution, and here you have zinc plus, and you have SO4 minus. And as current starts to run, SO4 minus ions, which are now the current carrier inside this battery, is going from the right, they're going from the right to the left. Now why would SO4 minus ions travel through an electric field that opposes them, that opposes their motion? And they do that because in doing so, they engage in a chemical reaction which yields more energy than it costs to climb the electric hill. And while a current is flowing, while the SO4 minus is going from the right to the left, you get fewer SO4 minus ions here. This liquid here remains neutral, so copper plus must disappear. And it precipitates onto this copper bar. So it's like copper plating. On this side, you get an increase of SO4 minus. Therefore, you also must get an increase of zinc plus, because again, this liquid there remains neutral, and that means that some of the zinc is being dissolved. So you get an increase in the concentration of the zinc. So the charge carriers inside this battery, the SO4 minus ions, travel through this barrier and they go from here to here. So they travel through an electric field that opposes their motion. And this happens at the expense of chemical energy. Now when the copper solution becomes very dilute, because all the copper has been plated onto the copper, and when this becomes concentrated with zinc plus, then the battery stops. And now what you can do, you can run a current in the opposite direction. So you can run a current now in this direction. You can force a current to run with another external power supply. And now the chemical reactions will reverse. So now copper will go back into the solution. So it will dissolve. And now the zinc will be precipitated onto the zinc. And so now if you do this long enough, you can run the battery again the way it is here. A car battery is exactly this kind of battery, except that you have lead and lead oxide instead of zinc and copper. But you also have sulfuric acid, like you have here. And a nickel-cadmium battery is well known. You can charge that too. These are the ones that are readily available in the stores. You can run your flashlights with these nickel-cadmium batteries. The symbol for battery that we will be using in our circuits is this. This is the positive side, and this is the negative side. This is a symbol that symbolizes that we're dealing with a battery. So let this point be B, and let this point be A, and here we have a resistor R. So we have a current going. The current is going in this direction. The current I. This could be a light bulb, could be your laptop, could be a hairdryer, whatever. That's your supply. If this R is not there, that means that the resistance is infinitely large. That means that the current that is running is zero.